Okay, welcome AP Physics Mechanics students. As you could see from the unit plan in front of you, we're about to begin our review for the AP test. But before we begin, I would like to first congratulate you on making it through a very difficult year. You've learned a lot of very complex physics, college level physics, and some of you have had to even learn calculus as we go along learning the physics. So if we were in school, I would ask that everyone give ourselves a round of applause. So congratulations for the tremendous achievement. But I also want to say something about the mindset that we need at this time of year. In my experience, I found that a lot of students often will view this portion of the test as a time to sort of relax a little bit. And they'll often say, well, we're just reviewing in physics. We're not really doing much. That is the wrong approach. If I were to hand you an AP Physics test right now, very few of you would get credit because of the ideas that we learned all the way back in September, November, October. Many of you have forgotten a lot of the ideas. They're kind of buried deep in your mind. So AP test now, all the hard work that we went through all year would kind of be for nothing. So this actually turns out to be the most important part of the year, okay? Because we've got to brush up our ideas, and this is where you're going to actually get ready for your 5 or your 4 or whatever, okay? So the analogy I like to use is, as you could see from the subtitle here, review the sprint to the finish line. We've run a marathon, almost an entire marathon. We've run through 25 miles. We have 1 mile left. Now is not the time to relax and slow down. Now is the time to actually give it your all and full out sprint toward the finish line. Okay, so the other thing I want to mention is about another mindset. As you know, the AP test is very heavily curved. A given year, if you get 68% of the tests correct, you get a 5 out of 5. On a regular school test, that's almost a failing mark. So it's a different mindset preparing for AP. You don't try and remember everything and review everything and look at all the details. What you have to do is be smart, be wise, and I'll help you with that. Try and figure out what the most important topics are. And then focus on those, the big ideas, the main ideas. Don't worry if you look back at a problem from 1985, for example, some oddball curve problem that's very difficult and a lot of people struggle with. Don't worry about that problem, okay? Because the chances are that's not going to come up on the AP. You want to look at the main ideas, what's most likely to be to show up on the test, and if you can master enough to get 70% of the test correct, you get a 5 out of 5 college credit. So that's what we're going to do in our review. We're going to not get bogged down on the details. So today we're going to begin the first topic of the review packet here, kinematics. And before I begin, I just want to give you an overview. You don't have to jot this down because this will come up in the notes as you know we go through them. But this is what's coming. In kinematics, we're first going to review the definitions and concepts behind the kinematics topic. Then we're going to review the equations that we learned. Then we're going to review free fall. Then how we graph various types of motion. And then finally projectile motion. So again, those are the things we're going to review for today. All right, well, let's begin. So, let's see. Okay. All right. Okay, so there are 3 ideas that we basically quantify when it comes to kinematics. A reminder, kinematics is just a mere description of motion, a mathematical description of motion. It doesn't answer the question of why things happen. That comes later in Newton's laws, energy, rotation. Right now, we're just going to mathematically write out what's happening to objects with numbers and formulas and graphs. So the first of the three main concepts, three different ways to describe the motion of an object, is x, the symbol x, which can stand for distance, displacement, or the coordinate or position of something. So it's kind of a little ambiguous. But recall that distance is always positive. It's a scalar. It does not have a direction. So like, for example, maybe today you jogged 5 miles. Maybe you jogged 2.5 miles to the north and then 2.5 miles to the south. That's a total of 5 miles. So that's the concept of distance. Of course, in our units, we express it or we measure distance in meters. The displacement is different. The displacement is like the net motion. So if you ran 5 miles north and 5 miles south, your displacement would actually be 0. So sometimes x is used for displacement as well. Another example, 5 miles north and 2 south, that is a displacement of 3 to the north. Or you can imagine x-axis with the origin 0, and x could be like where we are. Maybe we're at x equals 5 meters, then we go to x 4 meters, and so on and so forth. So if we want to describe the motion, we could give its coordinate as a function of time, and that would be a mathematical description of the object's motion. But another way to describe the object's motion mathematically is with the concept velocity or speed or velocity. Now here's the way we define it using calculus. It's the derivative of the coordinate x with respect to time. Or if you wanted to, as an algebraic formula, we have distance over time here, so we could express it as change in x over time, the meters per second. This would actually give us the average velocity for a certain amount of time, not the instantaneous velocity like this. So speed is like the meters per second, but without the direction, whereas velocity includes the direction as well. It's the vector, okay? So that's speed. Okay, the next concept, or another way we could describe the motion of an object is with acceleration, which is the derivative of velocity with respect to time. And since velocity is a derivative of x, then what we're doing is taking the derivative twice of an object's x-coordinate with respect to time. Those are two different ways to get acceleration. Or if you want, you can express it algebraically as the change in velocity per time. Okay, so that's, and the units of that would be meters per second divided by seconds, or as you no doubt know, meters per second squared. All right, so I just again want to explain some concepts. Okay, so the concepts that I want to review is like, when is an object speeding up or slowing down? A lot of times people think of acceleration being positive as an object speeding up, the acceleration being negative as the object slowing down, and that is not always the case. So this table here just gives us the concept of an acceleration and how its sign relates to the velocity of an object. So here's a column of velocities. Notice in the beginning the object's moving at 6 meters per second. As time goes on, the velocity goes 6,420. So the object's slowing down. The speedometer reading is decreasing. And if you did delta v over t for any pair of those velocities, you would find that the acceleration is -2 meters per second squared. So you say, oh yeah, look, see, negative acceleration means slowing down. But if you look at the table, after the velocity hits 0, the object momentarily has no movement, then the velocity goes -246, all negative. And if you look at the increment, how much the velocity is changing by every second, the acceleration is again -2 meters per second squared, while the object's speeding up. So slowing down, speeding up, the entire time the acceleration was -2. Okay? So, what is the pattern here? The pattern is that if acceleration and velocity have the same sign, the object's speeding up. In other words, if we have negative velocity and negative acceleration, notice we're changing the velocity by negative amounts every second, and we're already moving negative, so we're getting more velocity of what we already have. So we're going to speed up. Whereas if they're opposite signs, negative and positive, then the acceleration is the increment, and that's opposite of what we have, which means it's going to bring us to zero. So the object is slowing down. If they have opposite signs, they slow down. The other thing I want to just sort of remind you is that acceleration could be increasing or it could be decreasing. These are examples of a constant acceleration. You see that the velocity, the speedometer reading of the object changes by the same amount every second. And a lot of times people think when something is speeding up, they might say, oh, that's an increasing acceleration. No, it's a constant acceleration if your speedometer goes up by the same increment every second. 0, 2, 4, 6, 8, the acceleration's 2. Every second we gain 2. But this is an example of speeding up with an increasing acceleration. Notice the speedometer goes 0, 1, 3, 6, 10, 15. If you look at the increments, the increment between 0 and 1 is 1. Then between 1 and 3, the velocity increased by 2. Then it increased by 3. Then it increased by 4. Then it increased by 5. This is an increasing acceleration. So the object speeds up with an increasing acceleration instead of a constant acceleration. It's also possible to speed up with a decreasing acceleration. A lot of people say, well, doesn't that mean it's slowing down if it has a decreasing acceleration? No, it does not. Look at this velocity column here. I go from 0 to 10. So I gain 10 in the first second of motion. Then I go from 10 to 18. So I only gained 8. Okay. Then from 18 to 22, I gain 4. Then 22 to 24, I gain 2. Then 24 to 25, I gain 1. So see how I'm going faster, 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 but by a decreasing amount every second. So that can happen, particularly in the differential equations unit. We definitely had objects speeding up with a decreasing acceleration. Okay, so I just want to emphasize that. Okay, the next topic, next thing we're going to look at today is the equations. So we just learned about the concepts, x-coordinate, velocity, and acceleration we could give to describe something. We could also write out formulas for something. So this is a general formula, x equals x. You've seen these before. We've used these all year. So these are the kinematic formulas. Look those over. I'm not going to do any examples where I solve with these formulas, but you remember these where you have to pick the right formula, you plug in everything that you are given, all the data, and then you solve for the unknown, maybe like V0 or something, right? So I don't need to go over that. It's just algebra. But I do want to emphasize, these formulas are only for constant acceleration. Like when the speedometer in your car goes 0, 2, 4, 6, 8, right? It goes up by 2s, a constant amount. They are wrong, not valid, when we have a non-constant acceleration. Okay? If we have a non-constant acceleration, as we saw from the differential equations unit, you have to make new formulas. What I've done is I had dx dt is equal to velocity, right? So I moved the dt to the other side. I separated the variables, then I integrate both sides from x0 to x final, and from 0 timer to final time. And then I generate a new formula for the x coordinate. Let me show you an example. Here, let's suppose we had a v0 of 0. So the velocity was at, acceleration times time. If we use this concept where that you integrate velocity with respect to time, so we integrate this, we add 1 to the exponent, giving us t squared, and then we divide by that new exponent, giving us 1/2. So that's where 1/2 at squared came from. It was for only velocities that were proportional to time. Okay? But if we had velocity equal to some constant times time squared, so we had a time squared right here, Then when we integrate, we would have time cubed divided by 3. So we would have 1/3 AT cubed, right? So that's the formula if the velocity was squared instead of to the 1 power. So these, as I said during the differential equations topic, there's like the baby physics, right? So someone has integrated these for the students, but in general, if the velocity has a more complicated, different kind of form, we've got to do our own integration. And same for acceleration. Again, dv dt is the acceleration, right? So, and then I separate the variables, I move the dt to the other side, and then I integrate both sides from v0 to v final, from 0 to t final. If a was just a constant, that would generate this formula, okay? But again, if it's not a constant, you need to make your own new formula. Okay, so that's the calculus that can come into play in kinematics. Another topic for today is free fall. Okay, so free fall. First thing I want to mention is that free fall doesn't mean it's always going down, the object. Okay, people think falling means things go down. In physics, free fall could be something launched upward. And while it's rising and slowing down, that's free fall. The only requirement, I didn't write it here, is that the net force is just the force of gravity. Whether you're rising or falling, there's no air resistance, no rocket propulsion, it's just the gravity, the motion that just force of gravity creates. So I want to remind you that when you launch something up, whatever speed you're launching it up, maybe say 15 meters per second, when it comes back and lands without air resistance, it'll land with 15 but back downwards, so that's why it's negative 15 meters a second. And that the velocity at the peak is 0. Okay, so it gets to 0 and then it becomes negative. The other thing I want to point out is that the time on the way up is equal to the time on the way down. It rises the same amount of time as it falls. And those are 1/2 the total. So in other words, if this thing spent 6 seconds rising and falling, that means it would rise for 3 and fall for 3. And the big idea, the important thing, is that the acceleration on the way up, on the way down, and at the top is 9.8 downward, 9.8 meters per second squared. The difficult or challenging thing about free fall problems is, one of the difficult things is that very often they give you very little information, maybe just one piece of data. Like here's an example. I launch a ball up at 15 meters per second, and then the question asks, how high does it go? And so again, one piece of data. What you have to realize is, first of all, the acceleration is negative 9.8. You have to realize that when it reaches its final position of being at the highest that it goes, the velocity is 0, so you got to realize that. You plug in your positive 15 here, launch, the V0, negative 9.8, and you solve for h. So that's free fall, just using the formulas. And we could use all the constant acceleration formulas because the acceleration is approximately a constant 9.8. Okay, so, all right, this is going to be a little differently structured. I'm going to show both sides here, because what we're looking at next is how you can graph the motion of objects, the kinematic graphs. And to sort of understand this topic better, it's a good idea to split it into constant velocity and constant acceleration. Again, those are not the same thing. And the word uniform, that's just what the books and the tests tend to favor. Instead of saying constant velocity, be prepared for the word uniform, and you got to know that that's constant. So they're not the same thing. This is constant velocity, in other words, like your speedometer reading never changes. This is your speedometer reading is changing, but by a constant amount every second, as I mentioned earlier. Okay, so we're going to compare the graphs here for constant velocity acceleration. So these I've color coordinated. Let's suppose something is starting at the origin of the x-axis and it moves forward at a constant velocity. That would be this graph. Let's suppose something, if we got an x-axis here, maybe this is the origin, it starts at positive along the x-axis up here, and then it moves back toward the origin, like this. So the x value is decreasing with time. So that's how you'd graph those two motions. So that's why I said forward fast, backwards slow. How do I know that the backwards motion is slower? Well, the slope of this line is change in what's on this vertical axis, which is change in x over change in time. So that over that, change in x over change in time is the velocity of the object. So the steeper the line, the greater the velocity, the faster it's going. The less steep, the slower. So that's not as steep as that. Okay. The velocity graphs, constant, so they're horizontal lines. This is positive slope, negative slope. And both objects have, whether they're moving forward or backwards, they have zero acceleration because the velocity is not changing. If an object is accelerating, then what that means is the velocity or the speed is changing throughout the motion. And if speed is the slope, then that means that the slope has to change. In the case of something speeding up, moving forward and speeding up, the slope has to increase. Okay, so that's what we see with this green plot over here. Okay, so if you look at the slope right here, it's not very steep. A little steeper here, a little steeper there, it's speeding up. Okay, this is, so that's at the origin speeding up. This is something that begins away from the origin at some positive x coordinate, and it's moving backwards fast. How can I tell it's moving backwards? Well, it's not moving forward. It's moving backwards, coming back toward the origin. And fast because this line is very steep. If it were like a shallow line like this, it'd be going backwards and slow. This is backwards and fast. And it's slowing down because the magnitude of the slope is decreasing. Okay. To get the velocity here, we cannot do a simple slope. We have to first construct a tangent line. So I did it really light. I don't know if it shows up in the video. But you take a ruler, you draw a straight line, then you do rise over run of that tangent line, and that would be the velocity. Not very common on the AP. Okay, so how do you, for something accelerating, draw the velocity graphs? If the acceleration is constant, rather than being horizontal lines like over here, the lines have to be tilted. That's a changing velocity, or they could be tilted down. Okay, so this is zero velocity to positive, zero to positive. This is negative velocity to zero, so negative velocity to zero, okay? And if you think about, well, what does the slope mean here? It's the change of what's on the vertical axis over the change on the horizontal, and what's on the vertical is velocity, time over here. So we got velocity, change of velocity over time, and as you know, that is acceleration. This is tricky. A lot of students would think of this speeding up as being a positive acceleration and this slowing down as being a negative acceleration. Not correct, because they're both positive acceleration. The easiest way to see that is just to say, well, the slope of this line is positive and the slope of this line is positive. So they're both, the accelerations are both positive. But you could also think of it numerically. This is something speeding up, so its velocity speedometer reading is 0 here. And then it goes to some positive value. So I give an example. Maybe it goes from 0 to positive 15. That's a positive velocity change, and therefore a positive acceleration. Okay? This is going from a negative velocity to 0. So maybe it goes from negative 15 meters per second to 0. Do you add a positive or negative amount to this number to get to 0? You would have to add positive 15. So the velocity change is positive also. Therefore, the acceleration is positive. The way to see that from calculus is, remember, when you take the second derivative, which is what acceleration is, the second derivative of x, then if the second derivative is positive, that means the function is concave up. So that's concave up, positive acceleration. This is also concave up. Right? And then you go like this, right? If you continued. But it's concave up also instead of concave down. Okay, so that, therefore, is also positive acceleration. All right, so there are some graphs, how to interpret them, how to draw them. The next thing I want to review is the area of graphs. Okay, so we learned back on the first page that in order to get from velocity to get displacement, you have to integrate the velocity. And you may remember from your calculus that when you integrate a function, you're finding the area under a curve. And so if you're given a linear velocity like this, constant velocity for 4 seconds of 10, and then the object starts slowing down, and then it starts speeding up in the backwards direction, you could use the concept of area to find out its distance or its displacement. The way you do that is you imagine shading from the graph to the t-axis. So that shape. From the graph to the t-axis. From the graph to the t-axis, right there. Shade those shapes in, and then to find the distance, you just add up all the areas. So this is 4 times 10, base times height, the area of that rectangle. This is 1/2, 2 times 10, which is the area of this triangle. 1/2 the base is 2, from 4 to 6 seconds, that's 2 seconds. And the height is 10 meters second, 1/2 base times height. And then this area, also 1/2 base of 1 second, height of 5 meters per second. And we add all those up for distance, because remember, like I said, if you go jog 2.5 miles tomorrow, and then 2.5 miles backwards tomorrow, you jog 10 miles. Backwards motion for distance has no bearing. It still adds whether you're running forward or backwards for distance. So all pluses. But if you want to know the displacement, then you have to subtract off backwards motion. Remember, if you run 5 miles and then 2 miles back, the displacement is 3 miles from home, right? 5 minus 2, you're 3 miles from home. So we have this area plus this area. The areas above the axis are forward motion, so they add. But any area below the time axis is negative backwards motion, so we've got to put a minus sign here instead of a plus for displacement. So that's how you can find either the distance or displacement from a velocity graph. Okay, one last thing to review today. Projectile motion. Okay, so let's see, right about there. Okay, so first thing I want to just remind you that projectiles are things that are under the influence of gravity only. F net is equal to the force of gravity. So an airplane flying through the air is not a projectile because of the wing lift and the engine thrust. Okay, so you might say, well, how about if I kick a soccer ball? Well, technically that's not a projectile either, because there's gravity, but there's also air resistance of a soccer ball. So things around the earth are only approximate projectiles. Okay, but when you kick a ball or hit a golf ball in a physics problem, they are usually considered projectiles, meaning that we ignore the air resistance. And if air resistance is minimal, then or non-existent, then these are the two facts that in the x direction the acceleration is 0, whereas in the y direction it's negative 9.8 meters per second squared downward. And both of these things happen at the same time, and they don't affect each other. So if I shoot a bullet out of a gun, you think, oh wow, that's going to affect the acceleration of the falling. It is not. Okay? The forward motion, well, I guess I could say it this way. The forward motion and the falling motion, independent of each other. The acceleration of the bullet is still 9.8 downward. So what a projectile problem is, it's actually two kinematic problems happening at the same time. A constant velocity problem, sideways, and an acceleration problem, downward. Now, just a reminder, I could write the acceleration in I-J notation, I hat and J hat notation like this. 0 I hat, 0 in the x direction. Remember, the little I hat means x direction. And this J with a little hat on top of it, we say J hat. That's translated to say in the y direction. So this is saying 0 acceleration in the x, negative 9.8 in the y. That's how I could write this with one expression. All right, so There are two kinds of problems that we encounter when we're mainly. There's other kinds that you could be thrown at, but these are the most common. So the one is when you launch something off a cliff. Okay, you're launching it sideways, and it's falling a certain distance while moving a certain distance sideways. Again, I could express the velocity in one expression as the x velocity v0 I hat plus 0 in the j hat. There's no velocity up or down. So the most common way you calculate here in the y direction is you say the height is equal to 1/2 at squared. Remember the formula from earlier. The whole formula is x equals x0 plus v0t plus 1/2 at squared. But we can set this equal to 0, the x0, and the v0 is 0 because it's in the x, but in the y direction there's no velocity. So if we say y, those two terms are 0, and we just have the 1/2 at squared. Y equals 1/2 a, g being 9.8, t squared. You could put a minus sign for negative 9.8, but then the height would have to be negative because the thing fell down. Or you could leave both minus signs off, and that's fine. In the x direction, the most common thing to calculate would be this, x equals v0t. Remember the whole formula, x equals v0t plus 1/2 at squared. We could set this equal to 0 the moment the object is launched off the cliff. And the acceleration is 0 in the x direction, so all that survives is v0t in our calculation. And in the other kind of projectile problem is something launched off the ground. So maybe like a field goal kicked, right? Of course there's air resistance, but we're going to ignore that. Pretend there isn't a significant amount. The field goal or golf ball or whatever you're hitting, shooting an arrow, is going to go in a downward parabola like this. Okay, this is only a half parabola. So remember, a projectile problem is two problems happening at the same time, an x problem and a y problem. So knowing that, what we have to do is we have to split this velocity up because it's mixed. It's mixed in an x and a y together. So very often they'll say you launch something 20 meters per second, 30 degrees above the horizontal. That 20 meters per second is mixed, an x and a y. So we have to find the x and y so we could solve our two problems together. Using sine and cosine, you could find the x component of the velocity by multiplying by the cosine of the angle there, and the y by the sine, because this is the opposite side of the angle, this is the adjacent side. And we could express the velocity in ij notation. v0 is the vx I hat plus vy j hat. Instead of 0 in the j hat, we have both here, okay, horizontal and vertical. The most common calculation that comes about in the y direction is using v equals v0 plus at to figure out the time that this thing spends in the air. But you have to realize you're not going to use this 20 meters per second or whatever that is in this calculation. You're going to use the y, right? So the y is v sine theta. Whatever. If this is 20 and this is 30, that would actually be 10 when you do cosine 30 times 20. So this would be negative 10 and positive 10. Why? Well, when it lands over here, the final velocity is positive 10, negative 10, right? So negative when it lands and positive when it's launched. And then we have the minus 9.8, and we solve for the time. So if we use 10, we subtract, negative 10 minus 10 gives us negative 20 divided by negative 10. This would spend 2 seconds in the air. Another thing that shows up periodically is figuring out the height that this thing rises to. You could use 1/2 at squared. Remember, the whole formula is here. But if we use 1/2 at squared for distance and y over here, then what we're actually finding is the distance it falls from the peak when the velocity was 0 at that moment. So we would be finding the falling distance by 1/2 at squared, which is the same as the rising distance. So that's the easiest way to figure out how high it went. But notice, I'm using half the time. I said that the time here was 2 seconds in my example, so I'd plug in 1 second over here because it only falls for 1 second. rises for 1, total of 2. And once again, the x calculation is the same as over here. X equals v0t, okay, because again, the acceleration is 0 in the horizontal direction, and x0 we could set to 0, so we just have x equals v0t, okay? So that is our first review, kinematics. Okay, so see you in the next review lesson.